Bonjour, ma présentation aujourd'hui, c'est le sujet de la détection de la hauteur de neige, mais avec les drones et les caméras sur place, souterraines. C'est avec beaucoup de collègues et je vous invite pour une collaboration aussi si vous avez d'intérêt. Bon. C'est une plus vieille question, où et quand le neige fond. Et c'est un peu différent comme les mesures hypnotiques parce que c'est un problème d'échantillonnage. Ici, c'est un plus vieux rapport pour la bassin mousse en Ontario, écrit 1890. Et il dit qu'il y a un problème avec la fréchette. And really the problem is where and when the snow is melting. So, la première question de notre recherche, c'était si un UAV, un drone, comme on peut acheter à Best Buy, commercial, avec le logiciel Structure from Motion, nous avons fait Pix4D. Si c'est possible d'estimer l'échange de passé de neige en fonction de la couvert de sol. So we looked at three issues. The first is how complex this was, the accuracy of the elevation model when there's snow present, and the change of the accuracy of the change when there's snow present of the height, or when between snow and bare soil. This is an older study. I think there are many studies after this, but I think it's useful to just summarize this work because it's improving over time. Bon. There is theory. For those who have taken a course in photogrammetry, we know there's a relationship between vertical and horizontal uncertainty from matching points using photogrammetry. And as you can see, the relationship has three main factors: the uncertainty of the horizontal measurement. This is governed by the UAV resolution and its geolocation. For example, we have 2 centimeter data. The second is the height of the acquisitions, and the third is the number of acquisitions, K, that are overlapping. There is a small effect of the spacing along tracks, the baseline, but surprisingly not so big. And the bottom line is if you fly low, so you're at 50 meters, and slow, so you have many acquisitions, so 7 or 8 overlaps, you should expect an uncertainty of about 2.5 centimeters. So this is the theory, it's a hypothesis, and we set about to make experiments to try and test this. Bon. Notre site, c'était 2 sites en Gatineau, les champs, un plus plat et un peu rugueux, 3 à l'Acadie. C'était une forêt avec un purely clear cut with just some stumps, the next with shrubs, et le dernier, la forêt originale. We measured these for 1 snow season in Acadia and 2 snow seasons in Gatineau. Pour chaque site, they were entre 10 hectares ou je pense 60 hectares. Nous avons un ou 2 lains sur le terrain avec the snow stakes, les bétons. And at that point, we couldn't stand on the sites because it would make it easier for the UAVs to connect our footprints and make more matches. So we developed a method using telephoto cameras. But as you will see later, we've improved on this significantly. The result. So we use very simple equipment. I think today this equipment is much more advanced, but you can imagine if we do this with very simple equipment, we ran it all through the winter, very cold conditions. The only trick was low, and we had a 2 centimeter ground sampling distance, and we flew quite slowly. Geometric performance. À la gauche, c'est la densité des points per square meter in each image we were acquiring en fonction de la robustité de l'élévation. So how rough the terrain was on the x-axis. And you can see that as we get to rougher terrain, as we get to the forest and to the area where there are shrubs, we get much more point matches. So this K in the theory is higher. But when it's icy or when there's fresh snow, obviously there's less topography, less microtopography, and we have much fewer matches. This relates then to the question in the theory about the vertical versus the horizontal uncertainty. À la droite, la epsilon, c'est la vertical uncertainty from the structure from motion. And on the x-axis, the horizontal uncertainty against our control points, our validation points. Les couleurs, c'est jaune. Si c'est pas clair, it's overcast. And the size of the symbols are proportional to the number of matching points. And essentially, if you have enough points, you typically do well. You get within about 2 to 3 centimeter uncertainty in the x and the z axis. But sometimes, especially if it's cloudy or if you have few points, you will get a very large horizontal uncertainty. Interestingly, it doesn't translate into a large vertical uncertainty. And this is just because of the redundancy of the tag point matches, the other factors besides the sigma h trying to reduce the uncertainty. This is very useful information. I think it's much more developed now with more studies. But over snow, it's interesting to see that we get what we saw over basically snow-free terrain. OK, bon. La comparaison à la gauche, c'est la chance de la passée de neige in situ, souterraine, et avec le UAV. And you can see it's very close to the one-to-one line. The colors are solid if there is a case where it's overcast or icy snow. And generally, except for one case, we have an uncertainty over these transects. They're 15 meters long of less than a centimeter. So, when you average the random errors using these very low-cost systems, you can monitor snow depth change very accurately. Even at each of the posts in the transect, when we look at the root mean square deviation, so they're about a 10 centimeter footprint, we see uncertainties of less than 10 centimeters. And the more interesting question is the absolute depth, but it turned out to be a poor answer. À la droite, c'est le passé de neige, UAV, et sous mesure. And you can see that when the snow depth is very high, it's quite reasonable, except when you have these solid points, you have overcast conditions. But with low snow depth, UAV will tend to underestimate. And this is because the bare earth for the UAV is based on looking at vegetation, versus the bare earth for the snow depth is actually the bottom of our stake, which is in the mineral soil. So this is more of a question of how do you get the bare earth? And from this, we took out the message that maybe it's not that easy to get absolute snow depth, but relative snow depth is useful. And for that, it's quite useful if you're looking at things like monitoring flooding, where you want to know si la neige fond plus vite ou non. Mais vraiment, it was a bit disappointing parce que c'est difficile pour access les sites plus remotes avec les UAV. You have to be in line of sight. You cannot do it many times of the day easily, especially if it's snowing or raining. So it's quite limited operationally. I think it's more for research and for calibration or site selection. And after that, we step back. Here's the information if you need to see how we did things. It's in the presentation. It's been published, but we stepped back and we said, maybe we can do something simpler. Et notre question, c'est, la motivation, c'était parce qu'ils sont beaucoup des caméras souterraines pour beaucoup de choses, la gestion des animaux, pour the snowmobile trails from hunters. And we thought maybe it would be possible to look at monitoring snow depth using this technology. So, je sais, il y a beaucoup de publications et des méthodes pour utiliser le web cameras avec les règles pour la neige. Plusieurs de temps, ils ont les logiciels for finding the date, the numbers on the ruler or les indications, la graduation. Mais ça, c'est difficile pour j'ai dit, les tons complexes ou les signes, les forêts ou quelque chose where it's not easy to read things. So we develop a method which is based on very interesting technology from Quebec, which is the cycle, les postes pour les routes ici, des vélos, to try and use photogrammetry. So not to actually measure indicators of markers, but do photogrammetry. And the advantage is as it's possible to use this on cloudy days, on snowy days, and you can get this information. I will explain on the right how we extract the data. And it works to a reasonably good extent in forests. So here is a site in Parc Algonquin avec le Minister of Natural Resources Ontario. And again, it's processing many of these stakes. You notice one stake on the left was not processed, and it's automatically finding what it can do. The method. Première, c'est enregistration avec les web caméras, les images web caméra, parce que c'est possible pour le vent ou pour les animaux who disturb the cameras, and it will tilt. And so we want to recover this information. The second is, I will move my screen, I cannot see easily. The second is to verify the stakes actually exist. Again, they could bend, they could break. And the third is to process this stake dimensions to get the snow intersection from which we can get the depth of snow. So the registration works, it takes about 10 minutes. User takes one template, snow or no snow, and draws a box around each stake, takes about 5 minutes. Box around each of the blobs, the red markers. And because we know the dimensions of our stakes, we can get the dimensions per pixel. And c'est intéressant, c'est juste the fact that a line in perspective distortion, the proportions of distances along the line stay the same. So no matter how we measure the stakes, as long as they stay rigid, once we do this once, we don't need to do this again, because all the proportional distances, including the distance to the base of the snow, stays the same. That's the fundamental reason this is different from just looking at markers on a ruler. And you can see the registration. Cette logiciel, c'est la même pour votre cell phones. It's open source and very robust. For verification, it's a bit complex. What we do is we use a deep learning algorithm with convolution networks that are trained over time. So it actively learns because the snow can be present, the atmosphere can change, it can be snowing, the colors can get darker over time. So it's learning where the blobs are. Et ici à gauche, c'est si on fait un thresholding HSV, toi entre les 5 blobs rouges are the invalid. It doesn't see them really. Mais à droite, if you use the deep learning, even if there's snow on the blob, it can find it. And from that, it figures out the center essentially by looking at the shape and the edges of the blobs. So with this method, à la droite, c'est la forêt avec beaucoup des ombres and branches, etc., very complex. It finds almost all of the blobs on the stakes except for the top left where it's very dark. So you can see that this is something which can be done like a human would do it, but it's automated. When we know the blobs by photogrammetry, we just compute the relative distances to the base. And the trick is finding the base, l'intersection de la neige et les bétons. Mais ça, c'est pas plus difficile si on a un time series, parce que you can guess using a forecast where the snow intersection should be, and we use a Kalman filter to forecast where it should be. So we're searching for this over time. À la gauche, c'est un petit comparaison en un champ avec une station synoptique, Ministère de l'Environnement Ontario. Campbell CS50s in black, there are 3 actually. surrounding our site. The auto is what I showed you, and manual is where we use a person to detect the intersection versus our algorithm. You can see that the differences are relatively small, except for two periods, one when the snow is melting quickly, and the other when there is at the end of the season, there is again, it's always the CS. It seems like when it's changing a lot. I think this is due to the shading effect of the Campbell equipment. They're actually making drifts, and they're changing the microclimate around them. The intersection by the person is always larger because they are looking at the back of the stick instead of the front of the stick with the intersection. So there's a bias. À la doigt, c'est la forêt, c'est juste trois semaines, mais the manual and the automatic method are very close, and the rulers, which are manually read, are a little bit different, but I think, again, you see it's not always a bias, and this is because the rulers are catching different amounts of snow compared to our béton. So ça, c'est nous avons 2 années des mesures sur le terrain, et je pense que nous faisons un complete analysis, mais je pense qu'il marche comme ça, c'est très bon, je pense. Et nous avons, there's a very detailed document, including our equipment, how to install it, and the site on GitHub with the logiciel. It's very easy to use. It runs on your laptop. You can use it even if you're a student with your own sticks. You don't have to use our sticks. And so je pense que c'est bon. It's interesting to further compare this, and I would like to maybe collaborate with the previous talk on the comparison sites. But there are two interesting questions for the future. The first is, I suspect we don't need stakes. We could probably just use these cameras looking at trees or fence posts and measure snow depth, because really the blobs are not essential. It just needs to see 2 targets or 3 targets on a fixed rigid body that's going into the snow, and to measure from there. So this is one thing we're looking at, just to take pictures over time and get the snow depth without having any reference information after you calibrate once. La dernière question, c'est un challenge. Can you estimate SWI using such camera systems? And I will leave this as a challenge, but I think that there are a couple of methods that if you're inventive enough, you may be able to do it in a non-destructive manner. Merci.